to present data modeling methods. We will be using three aberration metrics in our analysis, which are R-squared, root mean squared error, and mean absolute error. So R-squared will be our main aberration matrix. So we will be using R-squared in hyperparameter tuning to select the best parameter for each model. Our target performance is 0.9 R-squared, means that we hope that our model can reach 0.9 R-squared, which is the same as our M. Then the cross-validation method that we will be using is four-fold cross-validation. First, we will split our data into two parts. One is 80% is the training data, 20% is the testing data. Then we will do four-fold cross-validation for the training data when performing the hyperparameter tuning. So why we use 4? Because as you can see, the testing data is actually consists of 887 instances. So we hope that the internal test set in the cross-validation is also having approximately the same number as the holdout test set. So that's why we choose four-fold cross-validation. Then we will create 4 models to test our data and select the best model. So we will be creating linear regression, decision tree, support vector machine, and random forest. After that, we will compare and select the best model. So now let's look at the results and discussions. I will be discussing linear regression and support vector machine. Another 2 models will be explained by one of my teammates. So for this is the summary of linear regression. So as you can see, all the attributes or features is actually significant because all the p-value for each attribute is actually less than 0.05. So all is significant, and then the most important feature is actually H. Why? Because it has the highest coefficient. So it means that when H increased by 1, the total UPDRS will be increased by 16.7570. And the least contributing attribute is sex. Sex 1 actually means female. So it means that when the patient is female, the total UPDRS will be 2.372 at less. Sorry, will be 2.372 at less compared to the male. So yeah, male is generally has higher total UPDRS than female. And from here we can also see that H, jitter, RPD, and PPE are having positive correlation with total UPDRS, while the other attributes are having negative correlation with the target. And one more thing to say is the R-squared for linear regression is actually very low. It's 0.1805. So it's not a good fit with the data. So now let's look at the diagnostic plots for linear regression. So from the plots, we can say that the linear regression is also not suitable for the data. Why? Because, for example, the normal QQ plot. So as we can see, the lower end and upper end of the normal QQ plots is off from the dashed line. So this means that our data is not following normal distribution, even though we have performed log transformation on the skewed data set. So it's still not following the normal distribution. And from this scale location plot, we also can see that our data is actually having is not having constant variance. So it also violates one of the assumption of linear regression, right? So this is the training and testing error of linear regression. So if you see R squared for training error is for training data set is 0.18, for test set is 0.14, and so we can see the R square is actually very low. So linear regression is actually underfit the data. So it also failed to achieve the target because our target is actually 0.5. Sorry, it's actually 0.9, but it's far away from our target. It's only 0.18. We also can see the similar trend in the RMSE and MAE. So as you can see, it's very high. The error is actually very high. So it's not a suitable model for this data set. So from the residual plot, we also can say that linear regression is not fit. It's not fit with the data, right? And especially the lower end and upper end of the data. So now let's look at support vector machine. So actually we perform parameters tuning for support vector machine, and we use radial basis function as the kernel for support vector machine. Why? Because we believe that our data is having non-linear relationship with the target. So based on our data exploration, so we believe that the radial basis function will fit better than the linear function, right? And then we will leave the sigma as its default values, which is 0.09639375. Then for the parameters tuning, we will tune the C values, which is the cause of constraints violation. So the greater values of C means that the lower generalization ability of the support vector machine. So we will tune these 10 values and then see which C values will produce the highest R squared. So based on this graph, we can say that the best C value is here. So what is this value? Is roughly about 32, right? So the best C is 32. Why? Because if we reduce the C or we further increase the C, the R squared will be decreased. So this is the optimum values. So the best parameters would be kernel is RBF, the sigma is the default values, and the C is 32 after performing the hyperparameter tuning. So after that, we feed the support vector machine with the best parameters, and this is the results that we get. So based on the results, we can say that SVM actually overfitted with the training data. Why we say so? Because the R squared for the training data is actually 0.7. It's not so bad, but R squared for the test data is 0.579, means 0.58. So it's much less than the training data. So we can say that the support vector machine is overfitted with the training data, but not generalized well on the test set. So it has been overfitting, and it also shows the same trend for RMSE and MAE. Why? Because the error on the test set is far greater than the training error. So it also failed to achieve the target because remember our target is 0.9 R squared. So it also failed to achieve it. So from the residual plot, we can say that actually SVM has better fit than linear regression because most of the residuals is within plus minus 10 values. So it's not so bad, but it also fails to correctly predict the values in the lower and upper end. So that's all from me. Thank you.